Hello, everyone. In this video, we're going to begin our work in section 8.5 of our workbook on Taylor polynomials and Taylor series. So the big idea in this chapter, or the big goal, is that we want to approximate functions using series. So let's get started in this preliminary example to give us a sense of what this means and why it might be helpful. All right, so in this example, we're told in part A to describe how to find a series written as P of x that has this form: C sub 0 plus C sub 1x plus C sub 2x squared plus C sub 3x cubed, etc., such that that series is actually equal to this more complicated function e to the 2x. And the reason why I say e to the 2x is more complicated is because this first series is just a polynomial. So meaning we just have sums and we are multiplying numbers together, while this e to the 2x is a function that's a little bit more involved. If you give me an x and fill in all of these coefficients, I could compute this p of x value. But if you give me an x, I'd have to use a calculator to figure out what e to that 2x is. Okay, so let's go ahead and get started. So let's start by just writing a little bit more notation. So what I'm going to do is just let the function f of x equal that e to the 2x function that we're concerned about. So now what we're doing here is sort of our first step is we want that first series, so c sub 0 plus c1x plus c2x squared plus c3x cubed plus c4x to the fourth plus dot, dot, dot. We want that to equal the function e to the 2x. So that means if we were to take a derivative, so we could call this like the second step, the derivative of my left-hand side here needs to be equal to the derivative of my right-hand side. So what does that mean? Well, let's take the derivative of both sides here. So when we take the derivative of that left-hand side, this c0, that's just a constant. So maybe I'll make a special note of that. These ci's are constants. And I might even call them coefficients because they are coefficients on my powers of x. Okay. So let's continue taking the derivative. So derivative of c0 is just 0. So then derivative of c1x is just c1. So this becomes c1. Derivative of c2 x squared. Well, I just take derivative of x squared and then I use that constant still there. So c2 times 2x plus c3 times 3x squared plus c4 times 4x to the cubed, etc. So that's going to equal to, well, the derivative of the right-hand side, e to the 2x is just e to the 2x for the derivative, but I need to use the chain rule, so I also am going to have a 2 that comes down here. So it would be 2 e to the 2x. Okay, let's just do this a couple more times because this approach, this method, taking derivatives, we'll see is going to help us determine what the c sub I coefficients are. Okay, so step 3, we're just going to do this again. So we're going to take the derivative again. So the derivative now, c1 is constant, so that would just be 0. So now we're going to get c2 times 2 for the derivative of this first term. Maybe I'll keep this in order so that so we see where kind of the derivatives line up here. Okay, so this was the derivative there. So derivative here is just going to be c2 times 2 plus derivative here is c cubed times 3 times 2 x plus c to the fourth times 4 times 3 x squared, etc. Derivative on the right. Oh, and we should have correct that exponent here. We still have 2x in the exponent. So good job if you already caught that. All right, so the derivative of 2 e to the 2x, well, we still have that 2 constant. Now, again, I just take the derivative of e to the 2x, so I need to use that chain rule. So I get another 2 e to the 2x. All right, so we can even write that 2 times 2 is 4. So I'm going to write 4 e to the 2x. All right, let's do this again. So now taking the derivative one more time, now that first term is 0. So now I just have C3 times 3 times 2 plus C4 times 4 times 3 times 2x, etc. Fill in my dot, dot, dots, dot, dot, dot. And then now when I take the derivative of 4e to the 2x, well, I'm going to have 4 times 2 because I'm using that chain rule on e to the 2x. So that would give me an 8e to the 2x. All right, so if we did this again, we'd see that that first term goes away, meaning this term would go to 0. And so I'd just be left with C4 times 4 times 3 times 2 plus, and then etc. All the rest of the derivatives. And on the right-hand side, I have 16e to the 2x. So we can use these derivatives that we just computed to find what these coefficients, c sub i's, are. The way that we're going to do that is to plug in a certain value of x in order to make it clear or to find an equality between C0 and a number, or Ci and a number. So let's go ahead and do that, and then you'll see why we did it, because it'll become apparent what those exponents are. Okay, so I'm going to just star this because it's like next step here. We're going to let x equal 0 in the above equalities. So what does that look like? So I'm going to write that out here. So let x equal 0. So in that first equality, if I have x be 0, notice that all of these terms with an x in it go to 0. So all of these will just be 0. These will all go away. So the left-hand side will be C0. The right-hand side will be e to the 2 times 0, which is just e to the 0, which is 1. So then that gives us our first equality, C0 equals 1. So now let's continue doing this for this second, third, fourth, and fifth equations that we have up here. At this point, also, I encourage you to pause the video and plug in x equals 0 for those remaining equations and then see what coefficients you get. And then we'll compare our work. All right, so when you're ready, let's continue. So then in the equation 2, when I plug in 0, all of my x terms become 0. So I'm just left with C1 equals, then the right-hand side would be 2 e to the 2 times 0, which would just be 2 times 1, so 2. All right, third equation, we just have all zeros but c sub 2, and that would be equal to 4 e to the 2 times 0, which is just 4. We're probably seeing a pattern here. So in the fourth equation, oops, and I made a small typo here. I actually had a 2 times C2. So we should get 2 times C2 here. Okay, so now we're on equation 4. So now when we plug in zeros for the x's, we're just left with 3 times 2 times C3 equals 8, or e to the 0, 8 times e to the 0, which is just 8. And then that fifth equation, we see we get just the term 4 times 3 times 2, c to the 4, c sub 4 equals 16. So I encourage you to pause the video at this point and just make sure you have these new 5 equations that are going to help us determine those coefficients. Okay, so notice that I don't quite have the coefficients solved, but we can go ahead and solve them. So C0 equals 1. C1 equals 2. So these two are already solved. But then we have C2 equals 4 over 2. C3 equals 8 over 3 times 2. C4 equals 16 over 4 times 3 times 2. Okay, so now what we can do is take the coefficients we've found so far and go ahead and plug that into our P of X series that we've set up. So I'll just make a note now. So now we can write P of X as, so P of X, recall, is this series here, which what we've assumed in this setup, or what we've required in this setup, is that P of X equals e to the 2x. So notice what we were doing there. Okay, so we can go ahead and fill in those c sub i's that we just computed here into that P of X series. So I'm going to write that out. So P of X as the following. And even I'm going to even just say P of X, which we know is equal to e to the 2x because of how we are computing those c sub I values, is P of X equals, so we're going to have c sub 0 plus c sub 1x plus c sub 2x squared. So that'll look like 1 plus 2x plus 4 over 2x squared plus 8 over 3 times 2, x cubed, plus 16 over 4 times 3 times 2, x to the 4th, plus dot, dot, dot. So at this point, what we want to do is look at the series we've created for our function f of x equals e to the 2x and see if there are any patterns that we can identify in this series. So take a moment, pause the video, reflect on the series we just wrote. Can you determine a general way to determine or to compute a coefficient? Well, let's look together. So let's notice where these numbers are coming from. So we see that the numerator in our coefficients are coming from this right-hand side. So 2, 4, 8, 16, 2, 4, 8, 16. So where were those coming from? Well, we were taking derivatives of our function f. So we see c sub 2 is just equal to our function evaluated at x equals 0. Because recall how we found that value of c sub 0 was we set the left and right-hand side of our first equation, we plugged in x equals 0 into our equation. So that right-hand side was just e to the 2 of 0 times 0, which is just f of 0. So this is just f of 0. Now, how did we get that numerator of c1? Well, we plugged in 0 into the first derivative, rather, of our function. So that was f prime of 0. We took the derivative of f, then we plugged in 0. The next numerator, we took the second derivative, and then we plugged in 0. That third derivative, c sub 3, we took the third derivative and plugged in 0. The c sub 4, we took the fourth derivative and plugged in 0. And then so now that we have a pattern for the numerator, and maybe we should make that pattern a little bit more explicit. So if we look at the third, we can just focus in on the third coefficient. The numerator is the third derivative of f evaluated at 0. So I'm going to write that down before continuing too much. So let's observe the following pattern. There is a pattern in the coefficient c sub I. So c sub I, we see that numerator looks like a fraction. The numerator is the ith derivative evaluated at 0. So just a note on that notation. So if you have a function where in little parentheses, there's a number, that means the ith derivative of f. And then since we have that parenthesis 0, we're evaluating that derivative at 0. Okay, so that's given us a good start to consider those numerators. So let's try to observe what's happening in the denominator of these coefficients. We'll notice that the third term has 3 times 2 in the denominator. The fourth term has 4 times 3 times 2. The second term, we could say, is just 2, and the first term just has a 1. So it turns out what we're seeing here, what the pattern is that that denominator is equivalent to the factorial of the index. So 4 times 3 times 2, that's just 4 factorial. I could write a times 1 there, but that doesn't change anything. Could write times 1, here I could write 1, or I could write 0 factorial. 0 factorial is 1. So then the pattern that we're seeing come up in the denominator for the ith coefficient is I factorial. So here we've created then a general form for the Ci coefficient. So this will allow us to determine the entire series by using this form for the coefficients. So far in this example, we've just determined the first 1, 2, 3, 4, 5 terms, but we can use this pattern that we just found to find all of the terms. Now in the next video, we're going to get into this in a little bit more detail and also look more general at creating series for given functions. Thanks for watching.